Thank you guys for all your love and support. In the last video, we have completed the digital electronics principle. Today we are going to start with logic gates and Boolean algebra. So what are the logic gates that we will use in our digital electronics? These are nothing but the inverter, the AND gate, OR gate, NAND, NOR, exclusive OR and exclusive NOR. For each of these gates, we are going to know about their symbol representation, then their truth table, then their operation, then their timing diagram. After that we will see some application and how to express in terms of Boolean algebra. So for each of the gate we will see all these points. Okay. Now let's first start the inverter. As you know, inverter is a circuit that will, what it will do, it will take the input and it will invert my input as in my output. That means it will do the function of inversion, or I can say it is a complement. So first let's take what is the symbol of this inverter. So this is the symbol of this inverter. There are basically two types of symbols that we use. One is using this triangle and bubble. Second one is using a square and after that a triangle and writing one inside this. This type of symbol, that rectangle with a triangle, that are used for International Electrotechnical Commission. This is the symbol used by the manufacturers. This is International Electrotechnical Commission. So they use this type of symbol. But for our study purpose, throughout this lecture, we will use this type of symbol. This is the general way to represent an inverter. Okay, that a triangle with a bubble. Again, this triangle with a bubble can be represented in two ways. One is first triangle then bubble, and second one is first bubble then triangle. So what are the difference between these two? This is nothing but my active low input. This is nothing but my active low output. What does this two mean? Active low, active low. This is my input side, this is my output side, and when this bubble is coming at the input side, I am telling it in active low input. So what do you mean by active low? Suppose this is a input signal. That is number of pulses applied to this inverter. Then what do you mean by active low input? From this input signal I am going to take the values of input for which it is low, the strength is low, or the signal level is low. So these are the range for which the signal is low. So this is active, means only these values are active, not these values. Okay. So when this bubble is coming first before the triangle, then this is the active low input, and since this is the input signal, and then I am going to take the time duration for which my input is low. Okay. Similarly, what do you mean by active low output? Suppose I applied some signal to this input, then what I got? I got a signal, digital signal, which is nothing but like this. Suppose anything that can. Then what do you mean by active low output? This is my output signal. This is the output of this upper inverter. Then the time interval for which my output is low, that is called active low. Similarly, for this case, this is the active low. This is my output, and I am going to take the interval for which my output is low. So you see from these intervals that below shaded this curly lines showing me the output that is low. Okay, these are the two type of representation. That one is active low input, one is active low output. We usually use this symbol in our study, but this symbol is used by the manufacturer, so they will use this type of symbol. So this is the symbol representation. So what do it mean? If I will give a 0 at my input, I will get a 1 at my output. If I will give a 1 at my input, I will get a 0 at my output. Okay, so based upon this value, we are going to write one truth table. What do we mean by truth table? Truth table means it will give the relation between input and output. For what input my output is coming for what value. Okay, so this is the truth table. This is my input side, this is my output side. If I am applying a 0, that is nothing but a low input, low level input, then I will get a high, that is nothing but 1 at my output side. If I will apply a 1, that is a high level input, I will get a 0 at my output side, that is a low level. Okay, so this is the truth table. This gives the relation between input and output. It tells if my output will 1, when my input is low. When my input is low, then only my output will be 1. Okay, so this is the truth table of this inverter. Now we'll see the operation, how this inverter operates. Suppose this is a signal that is applied to the inverter, and here is the inverter that is active. This is occurring bubble at output side, means this bubble indicates my inversion. Okay, this bubble do the inversion actually. So this is showing that active low output. So my output will be like this. Suppose this is a T1, this is a T0. So this is a T0, this is my T1. You see, for the time before T1, here the input is low. This is low, this is high. Since this is low, after the inversion it will become high for the time before T0. And from T1 to T0, my input is high, means it will invert to a value, input is low. And from T0 to moving further, my input is low, that means my output will become high. So it will just inverse whatever the input is given, it will just take the invert. So this is the operation how this inverter operates. And I already told that if I will apply, this is a high signal, positive going pulse, this is a positive going pulse, then I will get a negative going pulse at my output side. Okay, now we'll see the timing diagram. If you will remember what I told in the last video, that what is a timing diagram? A timing diagram gives me the relationship between two different waveforms. Okay, that is for which interval that my both waveforms are high or both waveforms are low, or some rising and falling timing, that for this time this waveform is rising, this is falling, like this. So this timing diagram for this inverter will give me the same expression. Like suppose I am going to take these two signals, that is, this is my input, this is my output. I am going to take these two signals. So this is a T1, this is a T0, and this upper one is my input, this lower one is my output. Then from these two diagram, from these two waveform, what I can elucidate, what I can draw, that what is given. You see, at time T1, my input is rising or not? It is rising from a value low to high. At the same time, my output is falling. Output is falling from a high value to low value. How I decide whether it is rising or falling, or the second term, that is leading and trailing. So when it will occur first, then I will say leading. When it will occur last, then I will say trailing. And if it goes from low to high, it means it is rising. And if it will fall from high to low, then I will say it is falling. So based upon this, I am telling over here, at time T1 both are the leading edge because they are coming first, but my input is rising and my output is falling. Similarly, at time T0, at this interval, both are trailing edge, both are coming last, they are trailing edge, but my input is falling and my output is rising. Is it clear or not? From this two diagram I can draw this data. So this for this inverter, this timing diagram is nothing but I will see the relation between input and output, and I can say from the two waveform or from the three waveform that what I can get from these two, whether it is rising or falling or for what interval. It is definitely whatever will be the input, the output will just inverse of that signal. It will no time it will become that they both input and output will same. Since this is an inverter, I am not going to get any two waveform input output, that will be the same for two interval. Okay. This is the inverter, means it is going to invert, it is going to inverse my input. So this is the timing diagram. Now we will see how to express this inverter. Okay, before going to express, let's see what is one application of this inverter. One application of this inverter is nothing but oneness complement. by using the inverter we can get the oneness complement. What do you mean by oneness complement? It is not there in your syllabus, but let me tell you, since it came into the picture, oneness complement means, suppose this is a binary number that is given 1011. Okay, I want to find this oneness complement means I have to change each bit. That in place of 1 I am going to write 0, in place of 0 I am going to write to 1, in place of 1 I am going to write 0. For this one, this is 0. This oneness complement means just changing each digit. If since it is 1, then I will become 0. I will write it 0, and when it is 0, I will write 1. So how this oneness? This is the format. This is the method to do oneness complement. So how I can use my inverter as a oneness complement? From these two you can easily see. If this is 1 0 1 1 is given, I am going to add 4 inverter circuit to each of my input. Okay, then what I will get at the output of this inverter is nothing but 0 1 0 0. So this is a simple application of this inverter, that is for oneness complement. Then the question might arise that what is oneness complement and why we are doing all this by changing all those values. Why we are going to do? We are doing because in our binary number system we can represent any positive number system with the use of these bits, but we can't write simply like the positive number. We can't write the negative number. So let's take this is 5. So how I can write this 5 in terms of 4 bit? This is nothing but 0 1 0 1. This is the representation of 5. You see, this is value 4, this is 2, this is 8, this is 1. So only I have to add this 4 and this 1, because here it is 0, it is 0. Okay, then 4 plus 1 is nothing but 5. Okay, this is the representation of plus 5 in binary. Suppose I have a 5-bit register, a register that will store the data. That is the register. Here it is a register, 5-bit register. This bit is 0, it indicating that my number is positive. This is called sign bit. Sign bit. Okay, it will represent whether my number is positive or negative. So this plus 5 is represented like this. This is the 4, this is the strength, that is nothing but the magnitude 0 1 0 1, which is a value 5, and this last bit positive 0, it gives me a value that it is a positive number. Then how we can represent minus 5? We can't use simply by using this formula, we can't write minus 5. So for that what we can do? We can use this oneness complement. It means just this is the magnitude, so just take the oneness complement of the each one, which is nothing but 1 0 1 0 0 1 0 1 means if I will convert 1 0 1 0. Then in place of sign bit, for positive number it is 0, and for the negative number the sign bit is nothing but 1. So the sign bit is nothing but 1. It means this 4 is my magnitude and this bit is nothing but my sign bit. So this is the representation of minus 5. So how I can know this is minus 5 or not? Since it is a 4-bit representation, my last bit it is coming 1 before this 4-bit. Since this is 1 means this value is negative. This one indicates that it is a negative number. And since it is negative number, then I am going to take the oneness complement of this one, 1 0 1 0, that I will get 0 1 0 1, which is nothing but 5. Okay, so this minus this 1 represents the negative number, and the digits that is present I am going to take again oneness complement to get my original value. This is the plus 5. So this is the representation of plus 5. And how to represent minus 5? Just in place of sign bit put 1, and what are the number that is given, just take the oneness complement. This is one application of oneness complement. We can see another use of oneness complement when we are going to subtract a bit high value than a low value. It means suppose I want to subtract 28 from 25. If I will subtract 28 from 25, then what I will get? I will get a value minus 3. Okay, so we are going to see this how to subtract that using oneness complement. So what is the representation of a 25? Is nothing but 1 0 0 1 2 4 16. Yeah, I think 0 1 1 24. Okay, this is the 5-bit representation of 25. This is nothing but 16. This is nothing but 8. This is nothing but 1. So 16 plus 8, 24 plus 1 is nothing but 25, and it is 4 and it is 2 that we are not including. Okay, so 1 1 0 0 1 is nothing but my representation of 25. Then how to represent 28? I can write 1 1 1 0 0. You see, this is 16, this is 8, this is 4. So 16 plus 8 24 plus 4 28. So this is the 1 1 0 0 0, triple 1 double 0, and this is the 1 1 0 0 1. This is the 2 number. I have to subtract my this number from this. Since this number is higher than this one, then I can do normal subtraction. Then what I can do? I have to take the oneness complement of this one. So 1 1 0 0 1 means that is the 25. And what will be the oneness complement of this one? Is nothing but 0 0 0 1 1. If I convert each one by 0 and each 0 by 1, then I will get this one. Then I am not going to subtract, I am going to add, because I have already taken one oneness complement. Then I will add, then 1 1 is nothing but 1 0. Then I will write sum as 0 and carry will be taken, which is nothing but 1, this carry. Again this 1 1 will become 1 0. So 0 carry over here. This is 1, this is 1, this is 1. Just I add these two numbers. Okay. Then what will happen? This number, whatever the number that is coming, here there is no further carry. Here the carry is 0. Okay, just remember, when the carry is 0, then I am going to take again oneness complement to get my actual result. When the carry is 0. So what will be the complement of this one? Which is nothing but 0, 0, 0, 1, 1. And since I have taken oneness complement, then I am going to write a negative number. So this is my final answer. It means it is a negative number, and this value gives me 2. It is 1, so it is nothing but 3. So this is minus 3. So you can check this is the minus 3. So what are the process? First represent this two number in binary form. Then take the complement of the subtrahend. It is called subtrahend. It is called minuend. Okay. I am going to take the oneness complement of subtrahend, that is nothing but 0 0 0 1 1. Then I am going to add these two. This minuend, then oneness complement of the subtrahend. Okay, after adding, if I am not getting any carry, means if the carry is 0, then I will take the oneness complement of this number. If there is a carry 1, then I have to add this one over here, and that will be the number. Let's see another example of this one. So this is using by this a large number is divided from the subtracted from the small number. Now let's subtract 25 5. Okay, I know the answer will be 16. That is simple, it is 16. Now we'll see how using this oneness complement it is possible. 21 means how I can divide this 21. 16 plus 40, 20 plus 1. Nothing but 1 for 16, 0 for 8, 1 for 4, 0 for 2, this one. So this is the representation of 21. How I have written? This is the 16, this is 4, 20, this is 1, 21, and for the 8.2 that is 0. Okay. What is the representation of 5? Which is nothing but 0, 0, 1, 0, 1. I am going to subtract. I am not going to subtract simple subtraction. I am going to do using oneness complement, and I will see whether my carry is coming or not. Then I will write 1, 0, 1, 0, 1 is this value. I will take the one for what is the rule? I have to take the oneness complement of the subtrahend, which is nothing but 1, 1, 0, 1, 0. This is the oneness complement of the subtrahend. Then I will add this is 1, 1, 1, 1, and 1 plus 1 is nothing but 1, 0, which is nothing but 0. Here one carry came. In previous case there was no carry, and here since one carry came, then I have to add this carry over here. Again, I have to add this carry. When the carry will come, I have to add. Then it will become 1 plus 1 is nothing but 1, 0. So 0 a carry is taken 1 over here. Then 1 plus 1, 1, 0. 0 again a carry over here. Then 1 plus 1, 1, 0. Again a carry over here. 1 plus 1, 1, 0. 0 again a carry over here 1. So and this 1 plus 1 is nothing but 1. So this is whatever the value that I will get. No need to put any negative number. No need to take any complement, because here carry came means this number is going to give me a positive value, and here say carry 0 means this number is going to give me a negative value. That's why I am taking oneness complement. Here no need of any again oneness complement, and no need to put any negative sign. So this value is nothing but 16 or not? You see, this is 16, this is 8, 4, 2, 1, 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. So since only 1 is there, 8 plus 2 power 4, that is the 16th answer. So you see. Okay, so this is the use of 1s complement in binary arithmetic, that is in addition or subtraction. Anyway you can do, you can see by subtracting a large number from a small number we can do, and to represent the sign component of binary digit, or that is the negative values of binary digit. So this is the 1s complement. So this is one application. Application is nothing but by just adding a inverter, whatever the value that is given, it will invert. Invert means it is nothing but the 1s complement. Okay. Now we'll see the expression. What do you mean by the expression of this inverter? We are going to this inverter in our Boolean algebra. What do you mean by Boolean algebra? That is there in our chapter also, Boolean algebra. Boolean algebra means it is the mathematical representation of our logic circuit. To represent our logic circuit mathematically, we are going to use Boolean algebra. So how to use this inverter in our Boolean algebra? For what do you mean by Boolean algebra means? We have to write one alphabet over here and some alphabet over here, and we have to put that symbol. So this is nothing but my input, this is nothing but my output, and this x is nothing but a bar. What does it? This bar means it is just the doing the inversion. Or I can say a bar, or I can say not a. This is the two representation of this symbol. This a and a bar over here, I can say a bar, or I can say not a. So this is the how we express this inverter in our Boolean algebra. For our Boolean algebra, if this is a input a is given, my x is nothing but a bar. It means my x will be invert of this one. Okay. So this is the representation of an inverter using in our Boolean algebra. This all about this inverter. Now we will see the AND gate. These all are gates. Where now we are going to see the AND gate and going to see all these form, all these truth table and operations. Okay. Now we'll see the AND gate. So actually what we are doing, the AND gate. First we'll see the symbol representation of AND gate. So this is the symbol representation of a AND gate. Here there is no bubble. Okay, just remember one thing. When there is a bubble means that then we are talking about that active low component. That when this bubble is before my triangle, then active low input, and this bubble is after my triangle, then active low output. And when there is no bubble, when this is the symbol only, it means if I am taking only at my input, then it is active high. And if I am taking at the output, that is equal to active high output. Input, this is output. It means whatever the value that I am taking here from here and here, that then I will take for the high component, for the time for which the signal is high, for this time period. Okay. And when there is a bubble, then I will take for the time period for which it is low, that is active low, and here it is active high. Okay. So this is the circuit symbol representation. So for this AND gate or this AND function, there can be any number of input and there is one output. So here we are going to take a 2 input AND gate to understood what is there inside the AND gate. So this is the symbol, that is 2 input, that is A and B applied over here. This is the output. Okay. So the output that we will see in our how to represent this output is nothing but A multiplication of B. Means this AND gate perform multiplication for a Boolean algebra. Then what is the truth table for this AND gate? We have already discussed this thing in our first video, but there are some other things that we forgot to tell. So this is the A, B, this is A dot B. Okay. Already I told you, if there are n number of inputs, then how many possible combination of inputs, which is nothing but 2 power n combination. When there are 2 input means there are 4 combinations. So what are those? 0, 0, 0, 1, 1, 0 and 1, 1. Okay. So how a AND gate work? It works, a output gives a value 1 when my both inputs will 1. When my both inputs will 1, at that time my output will be 1. And in all other case my output is 0. Okay. So this is the truth table of this AND gate, that when my both inputs are high, then only my output will be high. Suppose I have a 3n equal to 3. Number of bit input are 3. Then how many possible combination? 2 power 3 is nothing but 8. Then what will be the values? 0 0 0 with including A, B, C. 0 0 1 0 1 0, just increase 0 1 2 3 4 5 6 till 7. Since I have a n equal to 3, then I can have maximum 2 power n minus 1 decimal value. This you remember, I already told you, this is the maximum value that I can get. So 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. You see there are 8 values, but this value gives me a value 7. Triple 1 means 7. 4 plus 2 plus 1 gives me value 7. So when I have 3 input, this is the possible combination. Similarly, what will my output? My output will be 0 for all case. Only for the last case, when my all inputs are 1, then only my output will be 1. Okay. Suppose I have a 4 input AND gate. I have a 4 input A, B, C, D. A, B, C, D. Then how many possible combination? 2 power 4 means 16. Then starting from 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1, then again 1 0 0 0 1 0 0 1, everything. This part will be only replaced by 1 and all the thing that is there here will be same. So how to write this thing? If you might confuse between any two sequence, then just remember, you start with the value 4 0. Okay. Then for the LSB, alternate 0 1 0 1 0 1. You write like this. For this LSB, alternate 0 1. And for the next bit, you see here 2 zeros, 2 ones, 2 0, 2 1. Again 2 0, the next 2 will be 1. Okay. And for the next bit, here are 4 0 and then 4 1. Again here will be 4 0, then 4 1. Here it is 0 1 0 1 0 1. Alternate 0 1 for the LSB. Second one is equal to 0 0 1 1 like this. And third one is nothing but 4 0 4 1. And for the MSB, you see there are 8 0 and there will be 8 1. My last value will be 4 1, which is nothing but 1 1 1 1. It gives me a value 15. 4 bit means 2 power 4 minus 1 is the maximum decimal value. 2 power 4 16 minus 1 will give me a value 15, maximum value 15. 8 plus 4 plus 2 plus 1. Okay. Is depend upon my number of input. These are the possible combination of my input and accordingly my output. Here you see only for this case my AND gate will give me a value, output will high or 1, and for all the other case my output will be 0. Okay. So this is the truth table of this AND gate. And also the operation. So operation means if I am giving low at one input and low at other input, then what will be my output of AND gate? It will give me a value low, which is nothing but 0. From the truth table I am doing all this. And if I will give a value high and a low, then I will get an output low. If I will give a low input to the A and a high input to the B, then again I will get a low. And when only I will give my two input as high, then I will get my output as high. Okay, this is how this AND function operates. Then suppose I am applying a signal, I waveform like this. Okay. So this is my input is nothing but this is 0, 1, 0, 1, 0, 0, 1, 0, 1, 1. This is the input A. And my B input, let's take nothing but 1, 0, 1, 1, 0, 0, 1, 1, 0, 0. 2, 4, 6, 8, 10, 2, 4, 6, 9. Suppose these are my two inputs to the AND gate. And here this is the inputs applied to the AND gate. So what will my output? Then my output will become low for when there is either one low. It means since it is low and high, then output will become low. It is high and low, then output will become low. When there is one low also, then the output will become low. And when there are both inputs are high, then only my output will become high. For this interval also it is low because here it is low. You see for this interval for this interval my both inputs are 1, then my output will also become 1. And for the next two interval it is 0. And next for one interval, this interval, my output will become high, because here it is high, it is inputs are high, both inputs are high. Then it is low, because low and high will give me an output low, and next two case it will again give me a low. Okay, so this is the two waveform that is applied to AND gate, and this is the output that I am getting. And here you can see for this interval and for this interval my output is high, I am taking a high input. Since there are no bubbles, no bubble means I will take the active high output. Active high means I will take the high values, these values are high. And when there will be a bubble, then I might take the low values. Okay. Similarly, you can add any 2 to 3 signal. If I add another signal in between over here, then accordingly my output will change. So you see, for the time period when all the inputs that is applied to this AND gate, when they all are high, it is not that if, suppose I have a 4 signal that is applied, 5 signal applied to this AND gate, and for a time period T0 to T1, my 4 signal have value high, and at the time period 1 signal have a value low. Then also my output will become low. But remember, when my all inputs are high, then only my output will become high. Okay. So this is the how this AND operate. So and this from the time diagram you can say for the 4th bit my output is high, and for the 7th bit my output is high. So this is from the time diagram you can see this is the 4th bit, this is the 7th bit. Okay. Now let's see one application, one or two application of this AND gate. This AND gate used to enable or obstruct any signal. What does it mean when it enable or obstruct? It means suppose I want to count a number of frequency, that is suppose a signal that is passing, this is the signal, this is a train of pulse. Okay, this signal is applied to a input of a AND gate. Then this AND gate, this is one application. Then how this AND gate can be used? I am going to apply one enable signal. This is one enable signal that is applied to the second gate, second input of this AND gate. Then what will happen? You see, for this time period and from here to this time period, my one input is low. This input for this time period, this input is low, and for this time period, this input is low. It means my output will become low for this interval. And for the time interval when my enable is 1, enable 1 means it is allowing the signal. It is not that I am taking the AND gate, but I am allowing the signal. So for this interval I am allowing this signal. So this is the signal that will become the output. So from here, these 3 signal. Let's take this 3 signal. Now don't compare here, this is low and this is high, so it will become low. This is low, this is one signal, whatever the value, this is a signal, and when this is acting and it is enabling, it is called enable signal. So when this input, one input is enabled, then only it will transfer the whatever the pulse that is coming into the output. Okay, here I am not doing any AND operation over here, but I am applying to a AND gate and this enable is applied. For this interval, this is the number of signal that is passing to the output. So this is the signal. For this you can see this and these 3 signal that are passing to the output, and at the output I am going to use a counter. This counter will count number of pulses that is coming. To the counter I am going to add one register, or I can register or a decoder is there that will count number of pulse. Also it will show me the frequency display. It will display the frequency. Okay. Now let's understand what is happening. Suppose this time period it is enabling for a time period 1 millisecond. For this 1 millisecond, this second input is on. It means only for this time interval my input that is applied to the first, that will be transferred to the output. Then this is the time period for 1 millisecond. These are the number of pulses that is that are at the output side. That means there are 3 number of pulses at my output at this one interval. Then what will be frequency? Frequency is nothing but 1 by time period. So how many pulses are there? There are 3 pulses. 3 pulses per, sorry, that is 1 by, what is time period? Time period means number of signal per time, that is at 1 millisecond there are 3 number of pulses that are passing. it means that 3 will move to top and 1 millisecond will become kilohertz. So it will give me a frequency of kilohertz, 3 kilohertz. Okay, it means at this interval this is the frequency of my signal, that is the 3 kilohertz, and at my this is the frequency display. At the display I can see that frequency is 3 kilohertz. Now let's take for this one interval, unless there are 3, but let's take there are 10 number of pulses that are passing, and the step size is very less, the bit rate is very less, and 10 number of pulses are there in between this signal. Let's assume there are 10 number of pulses. So here will be 10 number of pulses. Then what will be my frequency? Frequency is 1 by t. Then which is nothing but 1 by 10. 1 millisecond upon 10 means at 1 millisecond 10 number of pulses that are passing. So 10 will move to the top, then it will become 10 kilohertz. So now this is the frequency. So based upon my number of pulses that are passing at the output, that will depend upon for which interval my signal is enabled. If it is enabled, then only the signal will pass. Okay. So this is one application. Now we'll see another application, that is that we can say seat belt alarm. Seat belt alarm. Okay, what does it mean? Suppose here is a AND gate, and to the AND gate 3 inputs are given. One input that is from the ignition switch. It means that suppose a driver that is he is riding the car, and this is the ignition switch, he on the key, and the car start ignite. It means it is on. So when it will on, then it will give me a value high. When it is off, the switch is off, or this lock that is off, it will give me a value low. And the second input is from the whether the driver is that buckled the seat belt or not. When it is buckled, then my output is off, or that is low, and when it is unbuckled, then it will give me a value high. Okay, this is depend upon whether the driver is buckled or not. And the third one is from here, that is a timer is connected. Okay, so let me tell you what is happening. Suppose the driver that ignite the switch, it means it is on. So if it is on, then this signal that is coming with a high value means it is coming 1. Okay, and at this time the driver forgot to buckle his belt to the seat belt. Then it is unbuckled. Not buckled yet means it is unbuckled. Unbuckled means it will give me a value 1. Okay, the driver has forgot to tie his that belt. Then suppose after the ignition, suppose for 30 seconds. After the timer is added, that for 30 seconds, if this after ignition some 30 seconds, this value will give me a value high. You on the key, and then after 30 seconds this value will give me on 1. When the 3 inputs are 1, that is applied to this AND gate, then it will give me a value 1. This 1 means here is a sensor, or that is a one alarm that will sound. It means the driver has started the car, but he forgot to buckle his belt. Okay, now let's take another instance. When the ignition is on, this is 1, and the driver, he is very cautious about the safety, then he already buckled, then this output will low. When he is buckled means already he tied the belt, means it is 0, and after 30 seconds the timer will automatically give me a value 1. After 30 seconds it will give me a value 1. Then this 1 0 1, what will be the output of this AND gate? It will become 0, because for AND gate, if any one input is 0 means output is 0. Output 0 means there will be no alarm. It means the driver is safe and he is very cautious about the rules. Then the alarm will not grow, or any sensor will not grow. So when the driver is unbuckled his seat belt, then only the output all will become 1, and then it will give me a sensor, or it will give me one alarm. So you see, we can use our AND gate in our car, or that is a seat belt alarm. Okay. Now we'll see that expression, how to express this AND gate in our Boolean expression. Okay. You see, this AND gate perform the multiplication. This form the multiplication. How? For binary number, if you remember, 0.0 means 0, 0.1 means 0, 1.0 means 0, 1.1 means 1. What is the dot? This dot is indicating this AND gate. if this there are two input A and B and this is the AND gate, then this is nothing but X, which is nothing but A dot B, or simply I can write AB, no need of any dot, or you can put dot. This dot means this is the AND operation, or I can say the multiplication is going on. So this is the multiplication of two binary number. So this is the same as my Boolean expression. In my Boolean expression, my this is nothing but X equal to A dot B. If my one input is 0 and second input is 0 or low, then my output will become low. Similarly, these four cases, that is RHS. This expression, this Boolean expression can use any three values. Let's take A, let's B, let's C. Then X will nothing but A into A dot B dot C, or simply A, B, C. If I take four inputs, then it will add another digit, another symbol, that is A, B, C, D. Okay. So this is all about the AND operation. Next, we will see the OR operation.